Okay, I think we're good to go. So yeah, welcome everyone to this afternoon's Tiger Supply Chain webinar. Today's theme is anti-fouling and anti-corrosion requirements of tidal turbines. Just a quick bit of housekeeping before we properly kick off. So thank you all again for joining. I'd just like to make a note that this webinar is being recorded and will be made available after the live event via the Tiger website. We will also make each of the presenters' slides available through Tiger as well. There is a Q&A functionality that we can use during the webinar. So please feel free to post any questions you have for our speakers via the Q&A functionality. You can also upvote questions that other attendees have posted if you're particularly interested in hearing the response to that question. And that will let us know which of these questions are most popular. If you're having any technical issues, then please feel free to use the chat function, and we've got someone on the other end there to support you with that. So just a quick run through the agenda. So shortly, I'll just do a quick introduction to the Tiger project for those of you who are not familiar with it. I'll then hand over to my colleague, John Walker, who will provide insight into the work he's been doing on the impact of surface roughness of tidal blades and their performance. We'll then move on to Raphael Coquet from HydroQuest, who'll give us some insight into what they've been doing for their deployment in Pample Brehat and their Ocean Quest device. We'll then move over to Dr. Tom Vance from Plymouth Marine Laboratories, who'll give us some insight into the work they've been doing on biofoul prevention, with particular emphasis in high energy sites, such as tidal energy sites. And then last but not least, we'll move to Charles Lebalieu from the French Corrosion Institute, who'll give us some insight into cathodic protection and what the requirements are there for offshore renewable energy. And then at the very end, as I've mentioned previously, we have a Q&A session where we'll run through hopefully all of the questions that are posed through the Q&A function. Any questions that we're unable to answer during this webinar, we'll endeavour to respond to after the event. Okay, so just very quickly, I'll introduce myself. My name's Theo van der Kammen. I'm the technical manager at the Offshore Renewable Energy Catapult, technical manager for the Tiger project. My background is solely in tidal stream energy. I've worked for a couple of technology developers, but now, yeah, based at the Offshore Renewable Energy Catapult, leading on the Tiger project. Tiger, the acronym, stands for Tidal Stream Industry Energizer Project. It's Interreg's largest ever funded project, valued at 45.4 million euros, of which just shy of 30 million euros is ERDF funding. It's a 4-year project, which was approved in July last year and will run until March 2023. Yeah, and as I mentioned, so the program is actually funded through the program Interreg France Channel England program, which is a collaborative cross-border project between the UK and France. So this is just a slide to show you. So the France Channel England region is shaded in dark green, so you can see it's stretches from Norfolk in the UK all the way along the south coast to the tip of Cornwall. And my office, yeah, is signpost by number 2 there in Hale in Cornwall. And it's reflected on the French side. So starting from Brittany, the Morbihan Gulf, and stretching all the way along the coast. We have a good spread of varying partners. We have 6 technology developers looking specifically at tidal technology. We have 6 universities, 3 on the UK side and 3 on the French side. And we also have 2 regional agencies involved in the project. You'll note that not all partners are based within the region. Some of them are based outside. So we have EMEC Orbital QED based in Scotland, Manchester University based in the north of England, Senio based outside of the area but still in France, and Monesto based in Sweden. So we have a whole range of partners involved in the Tiger project. The Catapult is the lead partner on the Tiger project. And as I've just mentioned, our head office and where the Tiger project is being delivered from is our office in Hale. Obviously, current circumstances mean that all of us are actually working from home. So I'm actually on the opposite side of the coast, on the south coast of Cornwall, directly opposite the arrow there. You can see on this map as well, so there are several tidal sites and development projects, as we call them, within Tiger. We have the Ramsey Sound site off the Pembrokeshire coast in Wales. We got special permission to include this project in Tiger. As you can see, it's outside of the region. Nevertheless, it has significant importance to the tidal sector, we feel, in the UK, being one of the very few grid-connected sites that are ready and able to accept new technology there. We have the PTEC site off the Isle of Wight on the south coast here in England. We have the Ras Blanchard, which is a very important site going forwards for commercial arrays. It's the world's 2nd strongest tidal resource. We have Pampel Brehat, which is owned by EDF, operated by Senio, and it is a test site which has seen the likes of Open Hydro and currently has HydroQuest deployed with their Ocean Quest 1 megawatt device, which we'll hear more about later on. And we also have the Morbihan project here, where Sabella are looking to deploy 2 250 kilowatt devices in the duration of the Tiger project. So there's a considerable amount of sort of development activity ongoing within Tiger. So what's the purpose of Tiger? At the moment, the market isn't particularly great for tidal stream in the UK. There's the route to market, as we call it, so the access to subsidies is extremely limited, if not impossible. On a more positive note, though, we've had the recent consultation from BEIS in the UK on the contract for difference subsidy mechanism. And subsequent to that, we've had another call for evidence from BEIS with specific emphasis on tidal stream and marine energy. So there are some positive signs coming out of government that we may hopefully have a new route to market, which will certainly help things going forwards. What Tiger is all about is looking at the levelized cost of energy for this technology. So in 2018, the Offshore Renewable Energy Catapult produced a report looking at wave and tidal and the cost reduction pathway. So we can see here that we had in 2018 approximately 10 megawatts of installed capacity, of which was costing on average £300 per megawatt hour. We believe through various initiatives that once we're at 200 megawatts installed capacity, that the levelized cost of energy will have dropped down to below £150 per megawatt hour. And again, by 1 gigawatts worth of installed capacity, we'll be down below the £100 per megawatt hour, which is competitive with nuclear power. What we don't know, and what hopefully Tiger might well be able to help pinpoint, is how quickly can we get down this cost reduction pathway. So we've got the green boxes, which are the areas of real focus for Tiger. So initial accelerated reductions. So this is basically looking at economies of volume, economies of scale, and accelerated learning. The best way of making these reductions is through project deployment. And so, as I pointed out earlier, we have several projects within the Tiger program, all looking to deploy up to 8 megawatts in the next couple of years. We have the learning by doing. So again, looking at optimizing, for example, deployment methodologies, retrieval methodologies, operation and maintenance, and collecting data for operating turbines, all with an ethos of shared learning between the technologies. And ultimately, we're looking to reduce the cost of capital. So by deploying and demonstrating these tidal technologies, we're able to boost the confidence of investors and give them a better understanding of what the technology is all about, where those challenges are, and how we're tackling them. So very, very briefly, we have 3 core work packages to Tiger. The first one is work package 1, and all about those deployment sites. We have Ramsey Sound, Pample Brayhat, where we have HydroQuest deployed now, and Monesto will deploy in 2022. The Morbihan Gulf, where Sabella will deploy 2 D08 250 kilowatt turbines. And then the Ras Blanchard, where we're actually looking to gain consent for 2 commercial tidal arrays, totaling a capacity of 24 megawatts. And the PTEC project as well. Unfortunately, the timing of it for it reaching financial close timed really poorly with the subsidy being removed in the UK. And as such, it's been in hibernation since, but we're looking through Tiger to reactivate and bring that site out of hibernation and accessible to project developers. Work package 2 is where we have a deep sort of forensic analysis on the systems, the components and processes that are used for these tidal technologies. And work package 3, we bring together all of the evidence that we've collected and all the information through work packages 1 and 2 to update the 2018 cost reduction pathway and hopefully provide the confidence and the evidence required for government support both in the UK and France. So we have a number of supply chain engagement activities throughout Tiger, of which these supply chain webinars are one. We're also looking to develop a range of equipment design specifications or processes. Excuse me. And to do that, we need to work with supply chain. So these webinars really are reaching out to interested parties within supply chain looking to branch out or branch into tidal stream. We'll be looking to put you in, in direct contact with technology developers to open up new discussions. So yeah, Tiger welcomes the opportunity to collaborate with other like-minded projects and associations. And if you'd like to discuss possible opportunities, please do get in touch. You'll find a lot of information on our website at interregtiger.com. And these are my contact details. So if you'd like to get in touch with the Catapult, please feel free to do so. And here's the contact details on screen. If I could just hand you over now to my colleague, John, who will take us through the first presentation. So over to you, John.
Okay, good afternoon, everybody. I'm John Walker, a project engineer at the Offshore Renewable Energy Catapult and currently based in our Glasgow office. Backgrounds in both the aerospace and renewable sectors, specifically in the area of fluid dynamics. In 2018, I completed a PhD researching the impact of marine biofouling on the performance of tidal turbine blade sections, of particular interest to this afternoon's webinar. In my current role at the Catapult, I lead the technical delivery of a variety of projects which support and develop future offshore renewable technologies. This first talk will look at the impact surface roughness can have on tidal turbine blade performance and help to set the scene for the following presentations on why fouling and corrosion strategies and prevention are required. Okay, so to open up, we'll look at turbine design. So an efficient tidal turbine design relies on the hydrodynamic blade performance. The majority of devices are lift-based and require an optimal lift-to-drag ratio for optimal power extraction and operation. However, this performance will be adversely affected by surface roughness, and this can come from a variety of sources. So erosion due to scour or cavitation, object damage from impact, or fouling from marine growth. And it's the impact of fouling where I'll focus today. The ultimate outcome of fouling on turbine blades is reduced levelized cost of energy. This is through reduced power output, through reduction in the optimal lift to drag ratio, increased operating costs to recover the performance, and due to being deployed subsea, you have limited opportunities for access for maintenance. Understanding and preventing this loss is critical. So we can look at, there's limited studies on fouling turbine performance and linking the two. It's a key industry concern for advancing the technology, and the effects are often both device and size specific, which we'll look at in a bit more detail in a minute. So very quickly, the mechanism behind marine biofouling. So marine biofouling is the unwanted accumulation of biological material in submerged man-made structures, but will only begin to interfere with the technical process once a certain fouling threshold has been reached. So this limit is something that we're quite interested in. So just to briefly go through the process, the initial conditioning film shown here in black is composed of dissolved organic matter, and it's absorbed onto the blade material within minutes of the device entering the water. And we're looking at scale of roughly 100 nanometers. And over the following hours and days, microbial biofilm forms up to the range of about 0.5 millimeter, and that consists of microfouling organisms, which include bacteria and algae. And then following the weeks and months, a third layer begins to develop, which is colonized by invertebrate larvae, which ultimately become your mussels, barnacles, and bivalves attached to the surface. So we end up with soft fouling, such as algae, we have hard fouling, such as barnacles, and we have microfouling, and we have macrofouling, the different scales of fouling as well in terms of size. So as I say, the challenge is determining what level of fouling you'd expect on the tidal turbine. Okay, so a level of fouling is inevitably currently on the device. The biological process starts as soon as the device enters the water, and the process is cumulative. Once the fouling process starts, the surface becomes more attractive to fouling species, and the surface becomes more susceptible to further fouling. And it's been seen that this fouling level varies across the blade surface. Specific organisms and the extent of the fouling are influenced by quite a wide range of different environmental and geographical features and factors. So these include the local flow quality and the turbulence level, the water quality, salinity, and the temperature where the device is deployed, the device material and the anti-fouling coatings that are used, the geographical location, the seasons and the breeding cycle of the species, and also how the device operates. We've seen in previous research that higher flow speeds are shown to result in thinner, denser biofilms, where the cell clusters are more resistant to detachment. And you can even see, for example, the same device at the same site but deployed at different times of year will have a different level of fouling after 6 months. And similarly, the same device at different locations would have quite a different pattern on it. The selection of a fouling coating is a key consideration for ensuring long-term operation, although the ultimate goal would be for the fouling not to be present. Okay, so looking at how the different methods of how you can investigate the impact of fouling, there's a few various methods ranging from numerical right the way through to deploying offshore. So just briefly describe each of these. So we can look at numerical applications such as CFD of the full rotor or CFD of the blade section alone. So taking a slice of the rotor blade and investigating the 2D performance. You can look at whole blade sections in wind tunnels, both statically and dynamically. And you can see here some different options. So you can put roughness tape or grit roughness, or also you can actually model different densities of barnacles, as you can see in this lower picture. In water tanks, towing tanks, you can look at scale rotor models, obviously quite a bit smaller than the actual device. And I suppose the ultimate way to find out what happens is actually to deploy the device. But potential commercial implications of this, developers, I imagine, wouldn't be too happy to share information on performance based on biofouling. And also, you really want to have a good understanding of either preventing the fouling or the performance impact before you deploy your device. For these first three options, the numerical, your wind tunnel testing, and your rotor testing, you require some key information. You need to know how big the fouling is, what the distribution is, and you also need to understand what your scaling effects are. So your fundamental fluid scaling values such as Reynolds number and your boundary layer thickness. These are all critical to be able to make suitable conclusions from your investigation. Okay, so looking at the blade performance, ultimately derived from lift and drag curves, and that combined across the blade gives you your driving torque, hence your power output. And what the surface roughness does, whether that comes from erosion or in this case fouling, it modifies the way the flow behaves, so it's transition, where it goes from into a turbulent flow, and also how the flow separates. And those in turn have quite dramatic impacts on both your lift and drag, which we'll see in a minute. Even with roughness of the order of tenths of a millimetre up to about half a millimetre in roughness, you will trip your flow. And that's roughly the scale of your biofilm. That's enough to have an effect. Pressure and velocity gradients around the blade, both chordwise and spanwise in both directions, play a role, and the roughness at the leading edge will result in quite a different outcome than if you have roughness at the trailing edge. So the position on the blade is very important from a fluid dynamic perspective. And also the two blade surfaces, upper and lower, obviously one sees suction, one sees pressure. You wouldn't expect those to have the same fouling distribution. So the critical parameters for these types of studies are the location and the extent of the fouling, the size of it, whether you're interested in the smaller scale biofilm, or are you actually interested in the larger barnacle fouling. It's not evenly distributed, as you can see on the figures on the right, which I'll give a bit more detail in a second. And the fouling and the roughness that you get on the blade is quite different from what you'd see on a wind turbine. Wind turbines predominantly have roughness around the leading edge due to insects hitting the blade, and you would be very unlikely to see such large scale roughness as a barnacle on a wind turbine. So what you can see on the right hand side is deployment of different coating samples and plates, and you can see how you get different distributions and densities. So this top image is just to illustrate how you get different densities and distributions based on the substrate. And this bottom right hand image is from the research I completed prior to joining the Catapult when I did my PhD. What you can see here quite clearly is, so if you look at these two arrows, you can see different areas of roughness on the blade. So down at the bottom, there's very little obvious roughness on the coating compared to the area by the upper arrow, where you can actually see quite a significant area of roughness. And again, it changes front to back, top to bottom of the blade, quite varied. And also in terms of barnacles, so this device had actually been deployed at EMEC about five years ago or so. What you can actually see by looking where the barnacles have attached is they are predominantly towards the trailing edge and back half of the blade. And the hypothesis of this is actually the shear due to the flow in the blade can have quite a significant impact on the attachment of the barnacle fouling. So I think the key message here is we need to consider densities and distributions when we assess performance. Okay, so I've now presented some recent experimental studies that are available in the literature just to highlight what can actually happen, first of all, to the lift and drag, and then secondly, to the power output of the turbine. So what we've got here is lift to drag curves. We've got different fouling levels and distribution. So the right-hand side is a study that was completed in 2014. I should also point out that these were not both by me. The study on the right-hand side is by me. It's just that Walker is a popular surname for people interested in tidal turbine research. This was completed by Jessica Walker in Australia. What you can see here is they investigated in the wind tunnel different levels of roughness, which would be comparable to your biofilm. So through from a clean configuration, increasing roughness up to what's the equivalent to about 1 millimeter height and roughness. And they also looked at the effect of roughness just in the leading edge zone and also widely distributed around the section. And what you can see is that the maximum lift decreases, there's a delay in stall, and the total lift force decreases for the worst fouling case by about 20%. Similarly, your drag increases from your clean case to your highest roughness case by over 100%. These blue arrows here just indicate increasing roughness. So we've got the clean cases and the black circles going out to your hollow squares. So that's what the most recent result really for distributed roughness, an experimental study. On the right-hand side is results that have been published as part of my previous PhD work that I mentioned. And what we looked at here is a single barnacle on the blade section. I should point out that this barnacle is not at all to scale, it's just an illustrative barnacle to show the position. So here we are about 60% chord. Quite interestingly, we saw no significant change to the lift or the normal force on the blade section, but the minimum drag force increased by up to 800%. So a massive increase in drag just due to by this single barnacle. And we got comparable results when we included distributed light roughness of a similar scale to the first study of about 0.5 millimeter to 1 millimeter. And just a little bit more information on this study. We actually put an instrumented barnacle, as you can see on the bottom right hand side. So we measured the pressure distribution around the body and around the blade in that area. And we were able to actually look at time varying and pressure distributions around the fouling to quantify that as well. So key message here in terms of lift and drag is that different types of fouling and their distribution will have different outcomes on the lift and drag, which in turn will influence what the power output of the turbine is. So next study, we'll look at power. So again, from the same first study as before, we can look at the power curves and the thrust curves. And then the second study is a more recent CFD study looking at the full scale rotor. So what you can see is the roughness, which is representative of that expected currently on a tidal turbine, will decrease this maximum power coefficient, which is directly linked to your power extracted, by up to 20% for the worst fouling case. And what it also does is decrease the thrust of the rotor, so the force trying to tip the rotor back. Similar results are seen in the CFD study, where at the optimal operating point, power coefficient decrease of approximately 11% is seen. But interestingly, what you can also see is that the operable tip speed ratio range narrows. So TSR, tip speed ratio, the ratio of the flow speed to the tip flow speed. It decreases for your optimal CP and the range narrows. So it's quite nice to have quite a wide kind of operating plateau. So for any changes in the flow, you're still operating at quite a high power coefficient. And you can see that this range narrows by, and at the worst case, this actually reduces to 20% of the clean case. So fouling and the roughness will have a direct impact on the turbine annual energy production due to the power being reduced. And therefore, that will also have quite a significant impact on the levelized cost of energy on these devices. So a few conclusions. Multiple interacting parameters influence blade surface roughness on the turbine. And if this roughness is present, then the turbine performance will be expected to degrade from initial fouling through to its full state. And the understanding of the fouling size and distribution is critical if you want to evaluate this performance. But as I said, the ultimate goal is to have a coating which prevents this from happening. CP power, so the power can decrease as much as 20% for the worst fouling cases. This will have a direct impact on both the annual energy production and the levelized cost of energy. And the optimal performance window for operation will narrow. And what all this does is it highlights the need for anti-fouling and anti-corrosion strategies and fouling prevention, which we'll hear about from the following three speakers this afternoon. So I'd now like to introduce Raphael Coquet. He's the Tidal Project Director at HydroQuest, and he will present the second talk of this afternoon's webinar on HydroQuest's strategy for tidal turbine corrosion resistance. So over to you.
Yeah. Good afternoon, everyone. Thank you very much, John, for your presentation. So, this session is about HydroQuest tidal turbines. First, I will present you our company, our first tidal turbine we deployed last year, and the next generation we will deploy in coming projects. And this presentation will focus on corrosion resistance, learnings from our first deployments, and the design and strategy on corrosion and anti-fouling resistance we plan to deploy for our next turbine generations. So first, HydroQuest uses hydrokinetics energy from river and tidal energy to produce electricity. We have proprietary design with vertical axis turbines. In fact, we have two columns of counter-rotating turbines, and that's our concept. The design's benefits of decades of learnings and experience from engineering and university research, and we are that's it. And the particularity of our design is that we don't need any pitch or yaw to control our turbine, so it's the turbine is fixed in the flow and can accommodate various angle of incidence of current. And so our history, the company was created 10 years ago. We launched our first river turbine in 2013 in French Guiana. It was a 10 kilowatt device which was deployed. We started to look at tidal sector in 2014 and started at this time a partnership with CMN, which is a shipyard located in Cherbourg. So we then in 2016 launched our first tidal project, which is called Ocean Quest, and the target within this project was to deploy a 1 megawatt device in Paimpol-Bréhat site, so in the Channel in Britain, in France. And this first turbine was deployed last spring 2019. Our strategy as our company and our manufacture facilities are located in France, and as we have one of the major tidal sites in the world, which is Blanchard, located really close to Cherbourg, we first focus in France. So our coming step are to deploy and validate and qualify our technology in the French area. And then we plan to deploy where the tidal sites are known, which are UK, Canada, and Indonesia. If we focus to France, the we have one major site, which is Rabanchat, with an installed capacity of 2 to 3 gigawatt, and one of the sites, which is from there in Brittany, which is 500 megawatts. Just to tell a little about our next step, we are working on the development of a pilot farm project of 14 megawatts. This pilot farm will be deployed in the Rabanchat, and the schedule is to deploy this pilot farm in 2023. And you just to finalize this slide, we have you see on this slide where is located the Pampa test site, which is where we have installed our first turbine. Word on our supply chain, we have a partnership with CMN, as I told you. They have a strong expertise in shipbuilding, so in associated and associated expertise, which are metal construction and assembly, qualification, and all that stuff. It's located in Cherbourg, so not far from Rabanchat. Yeah, and a particularity of tidal sector is that as our devices are quite heavy and big, our point of view is that they will be always assembled and manufactured really close to the final site of installation. This is a representation of our 1 megawatt device. So it's a device which has overall dimension of 24 meter by 12 meter high. It's 280 tons, the weight of the turbine. The turbine is mounted on a gravity-based foundation. You see on the picture with 3 feet. In each foot, you have ballast weight. For this one, it was cast iron ballast weight to stabilize the device under sliding and overturning. So the total weight of the cast iron ballast is 1,000 tons, and the weight of the foundation is 250 tons, and the overall dimension of the foundation is 28 meter by 24 meter. For this first device, we manufacture it in 20 months, and each of the rotating part, each of the rotor is 8 meter diameter by 4 meter high. We installed it in April 2019. I will go quick on this one, and it is in operation since June of 2019, and we plan to decommission and inspect it next summer. The initial plan was to decommission it this summer, 2020, but as it is operating well, we then postpone the decommissioning to have more data and to have more confidence in long-term deployment and wear of particular elements and so on. Regarding coating of this device, as it is a prototype and our first device, we only decided to have a design life of 5 years. So that's the point for this one. So we have a coating on all the ducted structure, which is an anti-corrosion coating. We have also an anti-fouling coating on quite a lot of parts for this first device. You see in green, it's all the surface where we decided to put anti-fouling. And we also ensure the corrosion resistance by adding some cathodic protection. So it was some aluminum anodes we put on some parts of the device. So you can see here some learnings of our first of this turbine. So you have on the right hand side 2 pictures. The upper one is on a part where there is no anti-fouling coating, and this is after 16 months of immersion. So you can see some fouling on the coating on the surface. And on the bottom, you see the blades after 16 months of immersion. So the anti-fouling coating is working very well. And we on our to just to make a parallel about what said John on the last presentation. We are let's say checking the performance of the turbine and see that there is no decrease of our performance of the turbine, and all our diving inspection are showing that the surface is really well for the moment. Regarding cathodic protection, there is consumption and wear on our anodes, but as we are designing it regarding DNV standards, the wear is lower than expected by the design. So it seems that the design is protection methodology seems quite appropriate. About the new generation, so this is our new generation. So we, for several reasons, about the increase, let's say the increase of performance, the reduce of weight, and the optimization of cost, we decided to delete the lateral ducts and to optimize all the ducted structure. So here you can see this this new design and this optimization. So the turbine will be 2.5 megawatts of nominal output power per turbine, with a 200-ton dry weight, with an overall dimension of 21 meters by 16 meters. And we will have the same kind of foundation as for Pampelware project. For the coating, one really important thing in tidal project is about the maintenance cost. Regarding, as you see in the previous pictures, the marine operation needs quite important vessels, which are quite costly. And we really need to optimize the maintenance frequency and to reduce it as much as possible. So this is an important challenge for the sector. So our strategy, and I hope we will succeed in it for the next generation, is to avoid anti-fouling coating, because the issue we have for the moment with anti-fouling coating is that we can't, any suppliers can't guarantee us that the anti-fouling will last more than 3, 4, let's say 5 years at the maximum. But usually they told us that it's going to last 2 to 3 years to be efficient. So this is, let's say, a big challenge, because we can't it would be quite costly to plan, to schedule maintenance and coating every 3 years. So the target is not to have anti-fouling to optimize maintenance cost and to have so only let's say corrosion resistant fouling, so a marine coating with epoxy layers on the green part, which is also ducted structure. In this kind of coating, we can expect that's a lifetime of 20 to 25 years. And so for information of for suppliers, if there is any in the webinar, we are on discussion with several suppliers, and you are invited to contact me if you want to discuss about this topic. Regarding cathodic protection, the design is performing following the NVID standard, and we plan to install standard anodes, and the design lifetime will be from 10 to 20 years. So we are working on it at the moment. And we plan to install anodes, a sensor on some anodes to qualify the real consumption in the site. A few words about the anti-fouling strategy. So what's important for us is not to have fouling on our rotor, on our turbine, on our rotor. We are then working on material and the finishing surface of our rotor, which is really confidential for the moment. Just to say that we are optimizing the surface roughness to avoid anti-fouling coating and the material, and that there is qualification ongoing in tank tests and in samples in the currently operating 1 megawatts device. So to conclude about our coating strategy, so we plan to do a marine coating with a design life of 20 years, with cathodic protection with a design time from 10 to 20 years. And development are ongoing to avoid any anti-fouling coating. Regarding maintenance cost reduction, we plan no maintenance on the turbine due to coating to reduce cost and maintenance frequency, and also to reduce cost when we are doing maintenance, because doing coating is taking quite a long time and is costly, and we have loss of production. Regarding other topics, we have collaboration ongoing on these topics with French Corrosion Institute, and HydroQuest is open to discuss about coating products or any other topic linked with cathodic protection and anti-fouling. That's it. Thank you for your attention. And, so now, Theo, I don't remember, it's Thomas.
Yeah, thank you, Raphael. Just a quick reminder before we move over to Tom, is that if you do have any questions for our speakers, please do use the Q&A function, and we'll endeavour to answer those questions at the end of the session. So Dr. Tom Vance, over to you.
Okay, thanks, Theo. Thanks for that very interesting talk. Just want to say thank you very much for the opportunity to talk. So thanks to Tiger, to EMEC and to Catapult for this opportunity. I'm going to talk about biofouling prevention in high energy environments, and looking at this from very much a sort of field-based approach. Bear with me 1 second. So just a quick word about our organisation, first of all. The parent organisation is the Plymouth Marine Laboratory, and it's an independent research charity. Our mission is to undertake interdisciplinary research to promote the stewardship of marine ecosystems. So a very pragmatic approach to how humans interact with the sea, and we just want to help people do that in the most responsible way and sustainable way possible. Within that parent organisation is the Centre for Marine Biofouling and Corrosion, which is the section that I'm managing. And we provide independent biofouling and corrosion control R&D and test house facilities to a wide range of sectors. And that could be shipping, defence, and we've done quite a few projects with the renewable energy sector now, oil and gas and aquaculture. So just to give you an idea of sort of who we work with and what we do, we work with people who have novel anti-fouling technologies and concepts. So organizations who want to screen their new prototype device against industry standards, we can help them do that. And we work with existing coating manufacturers. You might recognize a few coating companies there. We help them screen and develop their new formulations to make sure that they're doing what the manufacturers are hoping they do. And the most interesting bit of the job is providing bespoke biofouling management packages for end users. So people putting marine infrastructure in the sea, and they can't find an off-the-shelf solution, and then we can help them there. So that's who we are and where we come from. In terms of the we use some laboratory-based testing, but most of our work involves going out in the field and actually getting coatings in or as close to the operational environment as possible, and that's where we see the most learning coming back, and I'll touch on this in the presentation. So I just wanted to start off with a case study first of all, to give you an idea of the sort of work that we've been doing and the learning that's come out of it. This is work for Atlantis Resources. Atlantis had, I can't go into too much detail, but had unique engineering requirements in terms of the way they wanted to operate, which gave them an advantage competitively. But they were operating in an environment in the EMEC test site, or sorry, up in Orkney, which is subject to significant fouling pressure. So you've got lots of organisms, lots of larvae, and fast growth rates. And they also had significant time and tidal restrictions in terms of how and when they could operate, as applies to most tidal turbine deployments. So we worked with Atlantis to design a series of tests which would allow them to screen a series of different methods of designing subsea connectors. And we looked at different coatings, different configurations, and different ways of actually connecting cables up using connectors, and actually deployed those out in the field. We conducted some shipboard and laboratory-based assessment of these different options. And as a result, we were able to quite clearly demonstrate that there are advantages of different designs in terms of caps. Things like gap size and spaces which are available for fouling organism larvae to actually enter are critical in terms of design, as are the material selection and the anti-fouling coating choice, which we've been hearing about today. Another case study going back a few years now, when we're working for the REDAPT consortium. So the REDAPT project was the Reliable Data Acquisition Platform for tidal. And PML was tasked with testing coating performance in the tidal test site in Orkney at EMEC. And we were looking at characterizing coating abrasion and scour, so understanding how coatings actually survive in this harsh environment, and also producing a protocol for optimum coating selection. So how do you look at your device and decide which type of coating approach to take? So we deployed some test panels from lots of different coating manufacturers. We deployed some panels on the actual device itself, but the longest test duration was from panels which were deployed on standalone seabed pods, which were deployed in about 45 meters of water for ultimately 24 months. And the approach we took here was to help take a whole range of different coatings. So from the cheapest kind of off-the-shelf self-polishing coating that you might get from Chandler's that you could simply apply with a brush and roller, all the way through to, at the time, the sort of most high-end advanced anti-fouling coating provided by coating manufacturers. We gave everybody the same brief in terms of dealing with the coating manufacturers. We described the operational environment, and we encouraged the suppliers to apply their own coatings under control conditions to make sure there weren't any issues with application procedures of the coatings, and then perform the field test. And it was really interesting. We got a lot of learning from the project. So you can see here a quick before and after picture of the panels before they went in, all clean and shiny, and the result of being in the tidal stream for 24 months. I think from this picture it's quite easy. You could look at picture B and start to think, oh well, it's quite clear what I would go for in terms of coating strategy there. But once we started actually delving a little bit deeper and looking into the coatings in a little bit more detail, actually the selection procedure had a few more elements to it which weren't all immediately obvious. So first of all, we got everything back, which is no mean feat in that particular site. There was a clear difference between performance. And we were pleased that there was a consistent pattern between the replicates as well. So I'll go into that in a bit more detail. So yeah, so the organisms that can survive in a tidal race do very well there. So we've already heard about Corona hammeri, which is an acorn barnacle, which does very well in high energy sites. And it grows really, really quickly. And when we were monitoring these pods over time, and I think after the first flyby with an ROV, we started to see these blobs appearing on the antifouling coatings. And we thought, well, these can't be barnacles. They can't grow that quickly in this site, but they were. And you can see the size of them there. So in terms of roughness, you can quickly understand how these organisms have a very marked ability to affect the performance of certainly blades. There was really clear differences in terms of coating performance. I say we tested a whole range of different coating systems. And if you look at foul release coatings, so kind of silicon polymer type approaches, initially where they survived the mechanical damage of being in the site, they looked very impressive. You can see the image on the left there. You can practically see your face in that one. So after 24 months in the tidal stream, it looks pretty impressive. However, where those coatings became damaged, we saw really quite aggressive fouling occurring. And it actually seemed to go one step further, that if you look at this slide here on the top right-hand side, you can see the red anti-fouling coating. I'm not sure you can see my cursor here, and the white tie coat beneath it, which is heavily fouled with young recruits of this same species. So it looked like there's actual active preferential settlement going on the damaged coating on the tie coat. So these barnacles are able to either settle on imperfections in the coating themselves and then lever the coating up, as you can see in the picture here on the left, and start to peel the coating and delaminate it away from the surface. And once they've done that, they preferentially settle on the tie coat underneath. So if the same approach happens in terms of lifting up the coating and delamination, the only thing underneath that coating there is the anti-corrosive and then potentially mild steel. So you can quickly see how some of these organisms are very aggressive and can literally move their way through coating schemes, exposing steel and causing corrosion problems. So we did some work on coating roughness. We've already heard about roughness and how important that is. And I think it's just worth pointing out that when you're looking at coating selection in this first instance, the time zero coating roughness can vary quite considerably depending on which scheme you choose. So it's always worth bearing that in mind. There are trade-offs even at the cost stage, but also the performance of those coatings right from time zero. We looked at coating thickness as well. So of course we're looking at Raphael was just talking about long-term deployments of these devices, and most coating schemes that are commercially available at the moment are designed, as he's saying, for commercial vessels, which normally have a 5 or 7 year or 3 year even maintenance schedule, whereas we're looking at potentially deploying these devices for a lot longer. So we thought it was important to look at coating thickness, depending on the mechanism of the coating over time. We've got some quite clear information describing that basically there are very aggressive wear down rates for self-polishing coatings in these systems, in these environments. And basically we're taking these coatings beyond their design requirements and using them in a slightly different way. So we're going to expect different things from them in terms of longevity. So just as a quick summary to that particular bit of work, we were able to characterize the fouling potential at the site and give some real insight into the challenges associated with biofouling and its associated corrosion. We were able to use that information to inform how biofouling management strategies could be applied in terms of timing and when they're most efficient. It also became very clear that really you need to deal with this problem from the design stage. Trying to retrofit a solution is going to be really challenging. You need to consider things like surface topography, the roughness of components and the surface finishes, as Raphael was saying, to get the best from it. Just retrofitting what you believe to be the best anti-fouling coating is probably not going to get you out of trouble. We highlighted the requirement for coating selection. You've got to think about this and get this right at an early stage. And the optimum coating choice is not just about the cleanest after a couple of months. You have to look beyond that to see what the long-term best case scenario is for you. We also discovered that niche area awareness is really important. I'll talk about that in the next slide. It's beyond just the large surface areas where we need to be concerned here. Overall, the work was really, I saw it was a big step forward to de-risk, improve the reliability of these devices as a whole. So I just wanted to talk to you about a few sort of lessons from the field that we gained during these sorts of operations and just pass them on to you for those who aren't already aware. Niche areas, as we said, we've heard John was saying the importance of blade roughness and anti-fouling coatings in terms of the performance of the device, and absolutely there's no point in having a device which everything else is working but the blades aren't, of course. But what we really saw is it's the niche areas which are going to be a real concern here. So we saw evidence of fouling impacting on things like cameras, on heat exchangers, where the fouling was surprisingly prevalent and actually affected the ability of the device to cool itself where required. Sensors, so things like ADCPs, but when do you start trusting or distrusting the data produced from a device which is kind of covered in fouling here? Subsea connectors, we've already talked about those, these niche areas that are required to make that device work. And if you can't disconnect them, all of a sudden you've got a very expensive problem when you've got a DPS vessel on charter. And connection points for ROVs for deployment and connection as well. Again, all it takes is some fouling build-up in a particular niche area, and all of a sudden you may not be able to access your device for deployment and recovery in the way that you plan to do so. So biocorrosion, we're going to hear more about that later from Charles, I'm sure, but just some lessons that we saw. 316 grade marine steel didn't last long in this environment. So where we had barnacles settling on particular areas of 316, we saw really rapid corrosion. We're still looking at the mechanism there, but it was quite surprising to see how much marine grade steel, unprotected marine grade steel, I should say, disappeared after just 24 months. So if you start looking at that in terms of design spec and DNV standards, it just gives more insight that we're in a really challenging environment here that needs to be dealt with independently as a different site. You can't necessarily take oil and gas learning and apply it here. In terms of the coating summary, most coating selection is based on many different factors. It might just be what was available at the time, or what goes with the color scheme of the device, but it's usually not based on independent efficacy data. That can be one of the lowest sort of requirements, but we'd be keen to suggest that should be moved further up the list. I generally think from the work we've done that coatings of biofouling can be the Achilles heel of these marine renewable devices, and you can only really get the full impact of that once they've been in the water for 10, 20 years. You can take a certain amount of learning from other marine industries, as I say, in terms of coating selection, design specs, but what we're really seeing here is these are totally different environments, and we have to rewrite the rules to a certain extent and collect new data. It's worth saying also, beyond just operational performance, there is now increased scrutiny from a biosecurity point of view. So we're talking about moving big bits of fouled infrastructure from point A to point B. There will be, and already is, increased effort on making sure there aren't any biosecurity risks involved in doing that. So we're talking beyond just operational performance here as well. And as we're moving from prototypes and individual devices and talking about arrays, that's really when you start scaling up this maintenance issues, and you really understand how crucial the biofouling really is. So that sounds all sort of doom and gloom, but what can we do about it? What can we take from these lessons, and how can we improve what we do? Well, we've developed this sort of biofouling management approach that we apply through PM applications. It starts off with risk analysis. So if you're looking at a device or a component or a subsystem, where are the areas you need to consider in terms of fouling? Are there areas you don't need to worry about too much, or you actually really need to consider the whole area? So a desk-based risk analysis gets you a long way. Then looking at design and architecture, how can we at the design stage minimize fouling problems and make coatings easier and more effective to apply? Then looking at material selection, so what are we going to make those components out of? Of course, they need to fulfill the function they're designed for, but can we do things to improve our resilience to biofouling? So coating selection, we've already talked about that. Raphael talked about surface finish, and we see real potential there to giving you a little bit of extra time in the water without problems. It's also worth thinking about non-coating based anti-fouling systems. So there's lots of other anti-fouling approaches out there beyond coatings, and we should really consider those, especially for niche areas. Then move through to cleaning and operational procedures. The way that the device is operated and the way it's cleaned will also, if you have some element of control there, you can use those to your advantage in terms of keeping the device clean and operational for longer. And then of course, monitoring. You've got to know what you're doing and better feed that back into this approach to make sure you can adjust it and adapt it to make sure you're getting the best result. So take-home messages from what we've seen, really can't emphasize this enough, is consider biofouling corrosion from the design phase, and it'll just save you headaches and costs down the line. You've got to understand your operational environment. As John was saying, you see differences in the biology and the fouling rates, just even on hundreds of meters away on different sites. So you really got to understand what your site is like and how it operates spatially and temporally as well. I think you can get yourself out of trouble with a desk-based review approach to identify high-risk components and high-risk processes which are at risk from fouling, and consider that, let's say, from the design stage. Not all about coatings, as we said. There are, especially now with increasing regulation on biocidal coatings, manufacturers are turning to alternative ways of keeping surfaces clean and operational in the marine environment, and we would be crazy as an industry not to benefit from that. So we've got to think beyond just coatings here. Selecting anti-fouling technology based on testing and independent data collection seems like a good idea. Bear in mind all our sites are slightly different. We can't necessarily go on what the manufacturers of these coatings are telling us. And then, as we said, lastly, probably the most important thing is consider the management costs and maintenance costs when scaling up to actually understand the full operational cost of working in this environment. Okay. I'm going to end it there. I hope that was useful. And I'm going to hand over to Charles, who's going to talk about cathodic protection on offshore devices.
Okay, thank you, Thomas. I'm going to share my presentation. Okay. So just to introduce myself, I'm Charles Baller. I'm corrosion and marine corrosion and cathodic protection engineer at the French Corrosion Institute. So I'm going to talk about collection of data for cathodic protection in the field of offshore renewable energy. So first I'm going to introduce the corrosion and cathodic protection topic related to offshore structure and marine energy. Then I will explain how cathodic protection data can be collected in field for offshore sites. So I will show you a few results we obtained from previous campaign that shows the impact of the location, the temperature, and the flow rate. And I will say a few words about the possibility to also get cathodic protection data from bespoke seawater loop, and I will also say a few words about the modeling of cathodic protection and its integration. So as most of you know, offshore structures for marine energy are mostly made of carbon steel. The behavior of carbon steel in terms of corrosion is well known due to the huge experience from the oil and gas industry. So usually when carbon steel is used in immersion in seawater, it is protected against corrosion using a combination of coating and cathodic protection. So just to say a few words about the principle of the cathodic protection, it consists to apply a current to the structure to be protected in aim to lower its corrosion potential using anodic material such as aluminium or zinc anode, for instance, or power supply. So as shown on the chart, the structure to be protected here is connected to a sacrificial anode, which can be aluminium or zinc, for instance. The electrical connection between between both materials will lead to a galvanic cell, which produce a circulation of current that will decrease the potential of the structure to be protected and avoid any issue of corrosion on this structure. So this supply of current can also be applied using a power supply, which is called ACCP cathodic protection. So the cathodic protection is ensured for carbon steel when the potential reach value below minus 800 millivolt versus AgCl. So this is the cathodic protection criteria. So therefore, a good cathodic protection design should allow to provide enough current to reach this potential during the whole lifetime of the structure. So when the cathodic protection design is made, all the entrance data should fulfill this requirement. So the interest data have to be well selected. And the main interest data to consider are the current demand. So this current demand can be selected from standards or specification, and will allow to calculate the total anode mass to be used on the structure to be protected. So the most known and the most used is the DNV RPB401, which gave current demand depending of several sites, but mostly as a function of the temperature of the seawater. But this is the only variation that you can find in the DNV. So there is a limitation to the standard, which do not consider all the specificities of the project sites. And furthermore, it do not give a complete polarization curves for carbon steel and other materials. So when dealing with cathodic protection modeling, all the data are not available in the literature. So therefore, there is an interest to characterize that. So considering the main parameter that can affect the current demand to protect steel, which are the temperature and the dissolved oxygen, the flow rate, and the formation of calcareous deposit and or biofilm, which is time dependent. So considering these parameters that have a significant impact on the current demand, it is important to note that this parameter can lead to very different polarization behavior with regard to what we have in the DNV. So it exists a risk to perform an under or over design. So with under design, the structure won't be protected for the whole lifetime. The design will be shorter. And with an over design, you will have too many anodes on your structure and will increase the cost for nothing. So offshore marine structure can be expected to face high flow rates and especially tidal turbines. And high flow rates will definitely increase the current demand. So this is not considered in DNV. So it is a really test to assess for each exposure site what will be the current demand and the behavior of carbon steel or other materials if involved to perform an accurate cathodic protection design. So from this background, the French Corrosion Institute has developed a system able to collect long-term cathodic protection data directly on field and to compare them with key environmental parameters also collected on field. So the system consists of an instrumented array, which is presented here, which is equipped with several sensors to characterize environmental parameters such as the flow velocity, the dissolved oxygen, the temperature, conductivity, and salinity, and of course the cathodic protection sensors. So this cathodic protection sensor has been developed at the French Corrosion Institute in partnership with MKE. This sensor consisted in a cathode made of the material we wanted to assess, for instance, carbon steel. It will be put in connection with an anode through resistance, a shunt, which will allow to measure the current circulating between the anode and the cathode. So the galvanic coupling will be evaluated using this measurement. And in parallel, the potential of the cathode will be measured using a zinc pseudo-reference electrode, which is shown here. So this is autonomous data logger. So they are immersed in the exposure site, and they will be collected after the campaign to collect the data. And from this sensor, we are able to get the following information. So the evolution of the current density as a function of time, and also the potential of the cathode as a function of time. So with one sensor, it is possible to have one current potential couple. And by modifying the configuration of the sensor, by playing with the anode material or with the shunt value, for example, it is possible to have different current potential couple. And with different configuration of the sensor, it is possible to assess the complete electrochemical behavior of carbon steel, and thus to have the whole data for the cathodic protection design. So here is an illustration of the instrumented anchor line that has been deployed a few years ago. So it consists of classical anchor line with head buoy, acoustic release, ballast. Here, sample holder were also added for evaluation of corrosion directly on coupons, and the instrumented array, which was exposed at 1,000 meter depth and 200,000 meter depth. So this, for example, this anchor line will remain 2 years in the Atlantic Ocean, and several data were collected after that. So during the past years, several campaigns were performed all over the world. There was performed mostly for oil and gas structures, but we also performed campaign for offshore wind monopile in UK, and more recently with Sabella directly on the tidal turbine is a firmware in Britain. So I will now show you a few results we obtained from this campaign. So here we have results obtained in the Atlantic Ocean and in tropical sea here. So these data show the evolution of the potential as a function of the current density. So this is polarization curves drawn with the different sensor configuration after a few days of exposure. So here below 30 days. And after long-term polarization, so above 200 days. So one thing to know is that the carbon steel naturally immersed in seawater will have a potential close to -500, -600 millivolt without free in the seawater, without current, nothing. The potential will be here. If you apply the current to these materials, the potential will decrease gradually depending on the current density. And if you decrease sufficiently this potential, you will reach the potential protection of carbon steel, which is -800 millivolt. So below this value, there will be no corrosion of the surfaces of carbon steel. So your material will be fully protected. So the aim with these curves is to know how many current are needed to reach this potential. So what we can see here is that at the beginning of the polarization, during the first 30 days, about 200 milliampere per square meters were needed to reach this protection criteria. After long-term polarization, the current demand was only 100 milliampere per square meter. So the first information is that there is a decrease of the current demand with time, which is well known. So there is a process of polarization, so this is usual, but there is also an effect of the calcareous deposit that will form at the surface of carbon steel. This calcareous deposit will act as a sort of coating, so there will be less surfaces to be protected, more surfaces to polarize, so the current demand is lower. And if we compare that with data get from tropical sea, we can see here that the potential criteria is reached at about 80 milliampere per square meters during the initial state, so which is really lower compared to data from Atlantic Ocean. And after long-term polarization, the current density is also significantly lower, about 20 milliampere per square meter compared to 100 milliampere per square meter. So there is also a significant impact of the test sites. So here the impact of the temperature is predominant when we compare both sites, because in tropical sea the temperature was 30 degrees compared to 5 to 15 degrees in Atlantic Ocean. So in that condition, with high temperature, the dissolved oxygen level will be lower, and low dissolved oxygen lead to lower current density. so the current demand will be lower, so less anode are needed in tropical seawater compared to Atlantic Ocean. So this is what we get from this data collection campaign. I will show you also a few results about the campaign performed with Sabella, which is really interesting. So cathodic protection sensor were directly installed on the Sabella tidal turbine and installed in the Strait of Framber, close to Brest. At this location, really high flow rate can be encountered, close to 6 meters per second per moment. So this sensor were tested during 19 days for preliminary testing phases. And results are presented here. So here are the same type of curves. This is polarization curve. So the evolution of the potential as a function of the current density for 1 day here, 5 days, 30 days, and 90 days. So the main information here is that the standard sensor configuration used did not allow to polarize the carbon steel to the protection criteria of minus 800 millivolts. So you can see that data stopped between minus 600 and minus 650 millivolts. So that means that the sensor were not designed to support enough current density. So you can see that the current density reach were between 500 milliampere per square meter and 800 milliampere per square meter, which should be enough to reach this cathodic potential, but it was not the case due to the extremely high current demand. If we compare these results with results obtained at same time of exposure in Atlantic Ocean, we can see that after 19 days, with 20 milliampere per square meter, the potential of minus 800 is easily reached. Whereas here at 90 days, even with more than 500 milliampere per square meters, we cannot reach the protection criteria. So this is mainly due to the extremely high current demand due to the high flow rate. So these data are not considered in any standard. So there is an interest to assess them directly on field to optimize the cathodic protection design. So regarding this campaign, other sensors with different configuration were designed and have been deployed for longer exposure in aim to completely characterize this site. So just a few words about the possibility to perform laboratory data collection. So it is possible to build bespoke flow loops when the condition of the exposure site is well known. So it is possible to reproduce the main parameter influencing the current demand, so the flow rate, the temperature, the dissolved oxygen level, etc. And then to perform a bespoke flow loops with seawater and to perform potential and current measurement in aim to fully characterize the behavior of carbon steel or other materials in such condition, which should be representative of the field test site. And then when all data were obtained, so field polarization curves or polarization curves obtained in laboratory, it is possible to perform cathodic protection modeling. So to integrate by integrating polarization curves to the software console, it is possible to apply the electrochemical behavior of the carbon steel to given geometry, which is defined numerically. And then we obtain a mapping of the potential gradient as a function of the geometry. So it is possible to confirm that the structure is well polarized at any time of the lifetime, and also to optimize the cathodic protection design. So sometimes there is over or under design due to some factors that could be a security factor, for instance, and cathodic protection design can allow to refine the cathodic protection design. It is also possible to assess anode interference, for example, when using anode array as shown here. So a lot of things are possible with cathodic protection model. So to conclude and to summary what I've said during this presentation, since that the cathodic protection data from commonly used standard does not allow accurate cathodic protection design and modeling also. So instrumented arrays have been developed and deployed to collect long-term cathodic protection data in different field conditions. And we have seen that the flow rate very significantly affects the polarization and cathodic protection design, which cannot be done using standards. And also that the sites dedicated for offshore marine energy shall be further characterized for accurate cathodic protection design of the inner structure, especially for tidal turbines that can see extremely high flow rates. So just to finish, I would like to acknowledge the different member partner of the several projects for which I presented some results. And thank you for listening to me.
Thank you very much, Charles. I'd like to just very quickly say thank you very much to all the speakers. I've got to say it's been really interesting to learn just of the sheer importance of taking consideration of corrosion and anti-fouling for tidal turbines. It appears, no matter how well you design and get your tidal turbine to perform, if you haven't considered corrosion and anti-fouling issues, you're going to become stuck. Particularly the importance of including that quite early on in your design of your technology. And I didn't quite realize how destructive barnacles could be. So thanks for your insight in that. We're very quickly running out of time, but a quick question I have here, if I could pose to Raphael, was that you mentioned your cathode replacement was only possible every 10 years. Is this because it can only be carried out when the turbines are retrieved, or are you thinking that cathodes will be able to be replaced in situ in the future?
Yeah, from our point of view, as the slide tide's quite short for maintenance with divers or ROV. We do think it's cheaper and easier to replace anodes when we get turbine out of the water for maintenance operations. So that's why we are thinking of at least 10 years. And some anodes are located in area where divers can't go. So that's why. Okay.
And just one more question, unfortunately, due to time. And it's questions aimed at Tom. Is what's your opinion of the use of biocidal coatings and long-term pollution? And is this something that's being considered now? And are we trying to avoid the use of those biocides?
It's a good question. And yeah, ultimately, I think the whole regulatory framework is trying to reduce the use of biocides in the marine environment for good reasons. So there is a move to step away from biocides and coatings for sure, and not just the biocides, but also there's issues in terms of the polymers and microplastics and that sort of thing in coatings now. So looking at the impact of use of marine coatings from an environmental perspective is increasing, and there is tightening down on permitted use of different active substances. So at the moment, it's still sort of permissible, generally speaking, especially in open water environments. But yeah, if you're taking a long-term strategy, such as 25 years, looking at the life of the device, I think we really need to be moving away from biocidal systems where possible.
Great, thank you. Okay, I'm going to have to bring the Q&A session to an early close just because we've run out of time. But just very quickly, I'd just like to point out that we have two more Tiger webinars, the next one being on the 28th of October next week, looking into reliability and condition monitoring of tidal turbines. And the last in this series on the 30th of October, looking at supply chain opportunities for onshore and offshore mobilization for these projects within Tiger. So I'd like to say thank you very much to our speakers. I hope everyone will agree that the content was really, really interesting. And we will endeavour to answer those questions following the event. And thank you very much to all of our attendees. And I hope to see you at the next Tiger webinar on the 28th. So thank you very much.